Welcome, everybody. It's my pleasure today to introduce Matteo Pegoraro, who will be telling us about data analysis with merge trees.
Okay. Hi, everybody. Thank you for being here. I'm Matteo Pegoraro, and I've just started my postdoc in the TDA group in Aalborg University. So now I'm speaking from Denmark. First of all, I would like to very quickly thank the organizer for having set up this network and this seminar series and for having invited me. And I hope I can bring some positive contributions. So today, as the title of the presentation says, we'll be talking about data analysis with merge trees. And this presentation is going to be some kind of contain some collected topic from my PhD thesis, which I defended roughly 1 month ago. This is the outline of the presentation. We're going to have a very short introduction because I don't think that a lot of people listening are going to need a lot of additional motivation for being interested, at least to some extent, in topological data analysis. Then we'll start talking about merge trees, and I will present kind of the core of this presentation, which is a distance to compare merge trees, which I defined. This distance satisfies some properties that we're going to see, and I should have time to present a couple of applications in the end. So we can say that topological data analysis in recent years has brought many contributions and results to a field that we could call shape analysis. What do I mean by that? I mean all kinds of data analysis situations where we want to extract from data some kind of topological or geometric information, which, however, is invariant to some kind of transformations. So we have two kinds of variability in our data. One, which we are interested in keeping, and some other information which we want to factor out of the analysis. A very simple example, we can consider some functional data. There are situations, and maybe I'll give more details about that at the end of the presentation, in which we are given some functional data set, so some set of functions, and we cannot just compare them with some pointwise metrics, so embedding them in some LP space. But we would like to be able to stretch them, to shrink the domain of the functions, so also the graph of the functions, without the results of our analysis changing. Topological data analysis provides a lot of pipelines that can do such things, and mainly because it is built upon ideas, definitions, and objects from algebraic topology, which extract information from topological spaces, which are indeed invariant up to a huge set of transformation of the topological space. So what is the typical topological data analysis pipeline? Usually we are given some statistical unit, and we also have a topological space. And with the statistical unit, we produce a family of topological spaces which are included one in the other, and they are indexed by the real line. In a more compact notation, we can say that a filtration is just a functor, a covariant functor from the poset of real numbers to topological spaces, so that every arrow in the poset is sent to an injective map between topological spaces. Then, if we have a filtration of some topological space, it means that it's just a filtration which ends up filling this space. A typical example is if we have some bounded function defined on some topological space, we can take what is called the sublevel set filtration. So the preimage of the intervals which go from -infinite up to some threshold t. This is just an example that we can easily visualize. We have the blue function, and in thick red we have the sublevel set filtration. We can appreciate that the topology, the connectivity of this filtration really encodes the oscillating pattern of the function, and also that if we imagine about stretching or shrinking the domain of the function in some reasonable way, then this connectivity information doesn't change. Clearly, we can work also on other kinds of data, not only with functions. For instance, very typical the case of point clouds. We can inflate balls around the points of our point cloud with some fixed radius and take their union. If we then let the radius vary, again, we obtain a filtration of topological spaces. Okay, we have our statistical unit. We have produced a filtration of topological spaces. What happens next is that we usually apply some functor, some topology functor. Why a functor? Because it gives a natural way to kind of track down what happens to the information that we want to extract along the filtration. Probably the most used kind of the functor is the simplicial homology functor with the coefficients in some fields. And we end up with objects of this form. So they are functors from real numbers to vector spaces, which are usually called persistent modules. However, today we're going to be focusing on another kind of objects, which instead of applying the simplicial homology functor, work with the functor of path-connected components, which is this p-naught functor. In this way, we obtain a functor that goes from real number to sets, and usually these objects are called persistent sets. Especially when we have some kind of applied computational point of view, it's kind of usual to have some kind of finiteness condition on these objects, which for persistent modules would be tameness conditions, while for persistent set, we call these hypotheses, these conditions, constructibility conditions. And basically what we are asking is that at every point around along the filtration, we have a finite number of subset. We have a finite number of points in our set, and we only have a finite number of values, a finite number of points along the filtration around which our persistent set is allowed to change. Okay, so statistical unit, filtration, persistent modules, or persistent set. What comes after is usually a step in which we obtain some discrete, some computational representation of our object. For instance, in the case of persistent modules, satisfying some condition, this would be persistent diagrams or barcodes or other equivalent summaries. And so these are kind of a combinatorial finite representation of this object that we can use to carry out some data analysis because they are embedded in some metric space. Merge trees are to persistent sets what persistent diagrams are to persistent modules. So some discrete representation of those functors that classify those functors up to some equivalence relationship. Okay, so these are the objects that we are going to focus on today. How do we obtain that? Here we have a visual representation of a filtration. If we then apply the functor of path-connected components, we obtain this persistent set. We want to turn this persistent set into some discrete object that we can work on. We need to be a bit careful about giving definitions because we want to avoid this situation. We want to have a proper graph, or as the name says, a proper tree. So for instance, we don't want to work with objects of this form, but we want to always have something of this form, which is a proper graph. And the idea is that those two objects represent some persistent sets which just differ at a single point or at a finite number of points along the filtration. So we are not really interested in distinguishing between those two objects. And so we can always work with trees. We go back to the example that we've seen before. This is the sublevel set filtration, and this is the merge tree that represents the persistent set. We see that we have one leaf for every local minimum, one internal vertex for every local maximum, and the connectivity of this tree, the interconnectivity of these vertices, describes the merging pattern of the path-connected components. Without giving a formal definition, but we can still see that a merge tree in the end is just a tree with an height function defined on the vertices, which respects the poset structure of the tree, and the root of the tree is at height infinity. Clearly, we have started a merge tree from the sublevel set filtration. We can do the same with the point cloud, with the Rips filtration that inflates ball around our points. If we extract the merge tree, this object is usually called the single linkage hierarchical clustering dendrogram. That is an object that it has been around for a lot of years, and it has been used in many areas of science to work with clustering structure, to decide, to infer some clustering structure from a data set. And I think that this is very nice because with the language of TDA, we are able to formalize, to describe those objects in a more powerful way, so that now we can ask and answer to some questions that were not tackled before. For instance, issues about the stability of those objects. Okay, so now we have kind of the full pipeline. We started from a statistical unit, from our raw data, and we have obtained a data set of merge trees, and we want to work with this data set. You may ask, why do we want to do that? And the basic reason is that merge trees contain much more information compared to persistent diagrams. If we go back to this example for a second, suppose we have a point cloud with n points. We extract the merge tree and the persistence diagram. The idea is that you take the first path connected component that dies in your persistence diagram. These path connected components could have merged with any of the n-1 path connected components which are still alive. Similarly, if you take the second path connected components that dies in your persistence diagram, it could have merged with any of the n-2 path connected components which are still alive, and so on and so forth. And so we see that in that situation, for a persistence diagram of a RIPS filtration, we have a factorial number of merge trees which are represented by the same persistence diagram. And this kind of gives us an idea of how and how much information merge tree contain with respect to persistence diagrams. This is just an intuition, but this is kind of made formal in this paper by Justin Curry. So if someone is interested, they should read that. I also had some kind of personal motivations to work with merge trees, because basically I've been carrying out my PhD within a group of statisticians, and they were very used to clustering dendrograms. And so anytime I came up with the results on clustering dendrograms, so merge trees, it was easier to start a collaboration to apply them in their research. Clearly, you have to pay a price, and the price you have to pay in this case is that you're working with unordered, unlabeled trees, and so basically everything you do is going to be very computationally expensive. So we start with our data set of merge trees. At least we would like to know if the trees that we have are similar or if they are different. And how we do that? The idea is that we want to define a metric structure. There has been a lot of research on this topic in the last years, and we can divide the metrics that have been defined in two big families. A first family that you see on this slide is a family of metrics with very good theoretic properties, in particular, very strong stability properties, but they're very hard to compute. There are just very few exact algorithms around, and to my knowledge, they've never been implemented for real application because they're too complex. On the other side of the spectrum, we have some edit distances based on persistence pairs. These instead have very good computational properties, and they kind of can be described in this way. If you want another way to see the difference between persistence diagram and merge trees, is that a persistent diagram is just the set of the persistent pairs, the birth-death couples. The merge tree is the set of persistent pairs, but which inherit some hierarchical structure. These metrics try to produce something similar to the Wasserstein distance for persistence diagram, in which you just find matchings between the persistent pairs, but for merge trees. So they try to find matching between the persistent pairs which kind of respect this hierarchical structure. These metrics can be computed in polynomial time, and so they're very efficient. The drawback is that they are not stable. They do not satisfy stability properties. So there's not continuity when you go from functions to merge trees. This is why I wanted to come up with something new, something in between those two families of metrics, something which still has some stability properties, but which could still be computed for some applications. I resorted as well to edit distances, but I took a very different approach from the other edit distances, because I went through edit distances for weighted trees. So for the next couple of slides, we'll be focusing on weighted trees. A weighted tree is just a tree, and for each edge, we know how long it is. We have some function that goes from the edges to positive number that tells us how long is some edge. Edit distances are all set up in the same way. You define some number of modifications that you do on your starting object. Each modification has some cost, and you want to go from your starting object to some target objects, trying with a sequence of modification, trying to minimize the total cost. The edits, the transformation that I allow are, first, I want to be able to change the weight of some edges, change his length. So lengthen it, shorten it. Then I want to be able to remove some edge from the tree or to insert a new edge below some vertex in the tree. And these two families of edits are super classical. They appear in every edit distance, maybe with some slightly different name. For instance, the first edit, changing the length of some edge, is usually referred to as a relabeling edit. But then the main novelty of this metric is that I allow another kind of transformations, which to my knowledge is novel in scientific literature. And I want to be able, given an edge, to split it into edges by inserting an order to vertex. Or vice versa, I want to be able, if I have a couple of adjacent edges separated by an order to vertex, I want to be able to remove that vertex and merge the two edges. To have some length measure, we need to define some cost, and they are very natural. If we change the weight on some edge, so his length, we need to pay by how much we change the length of the edge. If I remove or insert some edge in the tree, I need to pay by how long was the edge that I removed or inserted. Instead, if I merge two edges or if I split some edge by inserting some vertex, I want this operation to be cost-free. I pay zero, nothing. This creates a lot of problem from the mathematical and computational point of view, because then I have a lot of trees which are within zero distance from each other. I can jump around the space of trees without really moving. But on the other side, this is fundamental for the stability properties of the metric. What I proved is that if we identify all these trees which are within zero distance of each other, so if we consider the quotient over this relationship of being within zero distance from each other, what we obtain is a metric on the resulting quotient space. This is just to give you an intuition on why this ghosting edit, this fact of splitting and removing vertices, merging edges is important. Consider this merge tree here and this merge tree here. We can consider this merge tree as the result as being extracted from just simply a monotone increasing function, which just gives this merge tree here. The sublevel set is just one path connected components which increases. This merge tree here, instead, we can consider it as being extracted from a very similar function, which is monotonically increasing up to some point where it has a small downward bump that creates this small edge here and then continues to increase. Those two functions are going to be pointwise very close. And so we want also this tree and this tree to be very similar if compared with our metric. In particular, it would be very nice if the distance between this tree and this tree would just be the length of this small edge here, which is created by the small downward bump. And with the edits that I set up, this is indeed the case. In fact, I can remove this edge here, and then we are left just with these two edges separated by this order to vertex, and I can freely remove this order to vertex to join the edges and obtain this merge tree. Okay, this is just to try to give you some intuition. So now we have obtained a metric for weighted trees. We need to transport it onto merge trees. We've seen that merge trees are just trees with some function defined on the vertices and this edge here that stretches up to infinity. How do we turn this tree into weighted trees? Maybe the first idea that comes up, a natural way to do that is just to truncate those edges that go to infinity and then take as weights the distances in the difference in height between the two vertices associated to one edge. And this indeed turns out to be a very good idea, because if we take a couple of merged trees, then cut, truncate at the same height, that the edge that goes to infinity, obtain the weighted trees and compare them with the edit distance that we defined, it turns out that this number is independent on the height at which we truncate them. And so we can take merged trees, truncate them, take the weighted trees and compare them, and this is a well-defined number. And so we can define the edit distance also for merged trees. We are going to see some properties of this metric. Luckily, this metric satisfies some good kind of computational properties. In fact, we can find the optimal path between two trees via some matching procedure. In particular, we can match every vertex either with some edit or with some vertex of the other tree. For instance, here, we start from this vertex here. We can delete it, so we can remove this edge here. Then this vertex here becomes an order 2 vertex, which we can remove from the tree. And lastly, we can merge. We can match this vertex here with this vertex here, which means matching this edge, this green edge with this green edge. And then we can match this vertex here with this other vertex here, which means matching this whole light blue edge with this light blue edge. And so what we obtain is basically a finite combinatorial space which parameterizes some edit paths, and we are guaranteed that within this finite combinatorial space, we always have at least one optimal edit path. And this basically is very good from all points of view. Then we can prove some stability properties of this metric. Clearly, we cannot expect this metric to behave like the interleaving distance between merged trees, which satisfies this inequality here. Why? Because the interleaving distance between merged trees works basically like the bottleneck distance between persistent diagrams. It's concerned about the biggest modification that you have to make is a sup metric. It takes the biggest modification that you have to make to turn one merged tree into the other. And this is why it's very stable. Our metric instead is more like the Wasserstein metric, because it collects all the local modifications that you need to do on your trees and it adds them up. And indeed, we obtain something which we kind of expect. We obtain a bound that depends on the pointwise difference between the function, but it also depends on the size linearly on the sizes of the tree. So whenever we have some bound on the size of the tree, we obtain a Lipschitz operator that goes from functions to merged trees. It was very interesting to me also to kind of deepen this relationship between the interleaving distance and the edit distance. And I was able to prove in particular that the edit distance is always bigger than the interleaving distance. And this has two consequences. First, the edit distance, but we were already expecting that, is more sensitive to noise. It's less stable. If we add noise to our data, the interleaving distance will vary more, will pick it up in some sense. But on the other end, if along our pipeline we have some way to deal with noise, we have some denoising procedure, maybe pruning the trees or working directly with our data, whatever, then our edit distance has a richer topology, has more open sets. So if we have some data analysis task in which we need to separate trees, arguably the edit distance is better just because it has more open set. It can better separate trees. I was also able to draw some comparison with the Wasserstein distance between persistent diagram, which for me was very interesting, but I think I'll skip it for now, and maybe if we have time in the end, I'll go back to it, also if someone is interested. And okay, now I want to make a point very clear. I was able to prove some decomposition properties for this metric, which means that instead of, if we have the optimization problem of computing the global matching between two trees, you can split it up in smaller subproblems and then aggregate the results to find the global optimal matching. And I framed this using binary linear programming. This means that this is not a computationally friendly metric. Why? Because binary linear programming is simply NP-hard. And whenever you're going to plug in this equation into some solver, this, especially the freely available one, they're going to use some routines which are, in the worst case, exponential, but they try and they do cut the computational cost with many tricks and heuristics. However, what I believe is a very positive result is that if we take the classical edit distance between trees, so no merge trees, no ghosting order to vertices, but just the classical one, which include also the edit distances, which I was talking about at the beginning of the presentation, then the latest and more efficient formulation of this classical edit distance for unordered and unlabeled trees in terms of binary linear programming is very similar to this complexity. It's just different by these two log factors. If we take out these two log factors, then the complexity is just the one of the classical edit distance. The edit distances which I talked about in the beginning then rely on the fact that for the classical edit distance, there is a constrained approximation of, if you want, a constrained version of the edit distance, which brings the computational cost into polynomial time. So this kind of gives me hope, even if in this implementation, my metric still has a very high computational cost. Since the implementation is not very far from the classical edit distance, this kind of gives me hope that also for my metric, there could be some kind of polynomial time approximation result. But on the other hand, this means that for being a metric for unlabeled trees, this is still pretty efficient. Also, given that we were able to prove some stability properties. Okay, then I went on and I kind of started investigating the metric space that we obtain with this distance. Why? Because I wanted to see if I could define some kind of additional structure to use some kind of more refined statistical tools and not just taking distances between trees. This has proven to be a very difficult task, and especially in a global way without kind of considering subspaces. This space behaves quite badly around in every neighborhood of every tree. We have unbound, the dimension of the trees is unbound, and this means that we lose completeness and also compactness, and also uniqueness of geodesics is an issue everywhere. However, if you are able to have kind of an upper bound on the dimension of the trees, we are able to retrieve some many useful properties like completeness. We are able to characterize some compact sets, and for certain geodesics, we can parameterize them with a couple of straight lines into different Euclidean spaces with the one norm. And this is just a picture kind of showing the different strata given by the dimensions of the trees. You have geodesics which cross straight and then go back, geodesics which are just contained in one stratum, so in which the dimension of the tree is constant, and it's a very complex space in which these strata interacted in a lot of different ways. Okay, I'm not commenting on this picture, but it should show the thing that some geodesic can be parameterized with a couple of straight line in Euclidean spaces. With all these results, what I was able to prove is that at least in this space, metric space of merged trees, we have some notion of mean, because the Frechét functional, which gives a generalization of the Euclidean mean, always admits at least one minimizer. So we have some kind of notion of average of mean in the space of merged trees. I also propose some approximation procedure. I still haven't studied the convergence properties of this approximation procedure, but I proved that it's just an iterative procedure, and step after step, the value of the Frechét functional cannot increase.
Matteo, can I ask a quick question?
Yeah, sure.
So do you know, are means not necessarily always unique?
Yeah, no, it's as a consequence of the fact that you have often more than one minimizing geodesic, then also the Frechét mean is not going to be unique. And yeah, especially the fact is that you often can match two trees, either just modifying kind of the length of the branches, or you can squeeze, delete some branch, and then regrow it by swapping father and children relationships. And this is kind of what creates some problems, but at the same time, this is also what gives the stability to this metric. Okay, because some of the other edit distances, in fact, have some techniques like barycenters, PCA, and other stuff, because basically they don't really allow the second kind of geodesic. So the one in which you delete some edges and then regrow them to swap father and children relationship. But this is fundamental to have stability.
Thank you.
Okay, now we have time for the applications. The first one is in the field of functional data analysis. And here we kind of go back at the beginning of the presentation. As I said, there are situations in which you are given some data set of functions, and you cannot simply compare them with a pointwise metric. You cannot just take a pointwise comparison between the two functions for some reasons, and we're going to see an example in a minute. So usually statisticians select some group of parameterization functions and try to align those functions by changing their parameterization, so just like kind of squishing or enlarging the domain, trying to maximize the pairwise similarities between those functions. For instance, here you can see that going from the left to the right, functions oscillate more in a similar fashion on the right. The group of functions have a more similar oscillating pattern on the right compared to the left. And so the statisticians change the parameterization of those functions and then carry out their analysis after the reparametrization step on the reparametrized functions. We have seen that the merge tree of the function is indeed invariant. We can take the function, and if we stretch it or shrink it in some reasonable way, then the connectivity of the sublevel set will not change. And so the merge tree simply doesn't change. And so we do not have this kind of problems. We do not worry about the parameterization of the function. We consider a benchmark case study in this kind of field of functional data analysis, which is a data set which was realized by Politecnico di Milano in collaboration with an hospital, Niguarda Hospital in Milano. And it's a data set that collects the 3D reconstruction of 65 inner carotid arteries, which were suspected of having cerebral aneurysms. Then from this 3D reconstruction, some functional covariates were extracted. The key point is that in these 3D blood vessels, and so also in the functional covariates, there is a lot of variability which is unneeded, which we want to factor out of the analysis. In fact, the aim of the project was to study the geometry of these blood vessels in relationship with the eventual aneurysms that were present. But these 3D shapes do not depend just on the aneurysm, that if it's there or if it's not there, but also on the inner morphology of the head of the patient, and also on the position of the head of the patient with respect to the tool that is taking the angiography. So a priori, there is not a correspondence between the points of two different reconstructed inner carotid artery. And so we cannot just take the functions defined on those objects and compare them in a pointwise fashion. So there is this paper, which is a kind of a benchmark paper for this data set, in which they tackled a classification case study with the classical techniques that I showed you before. They selected some group of parameterization function, which, if I'm not wrong, is they were affine functions. They aligned them by maximizing pairwise similarities, and then carried out some classification on this aligned functional data set. Basically, we reproduced the exact same pipeline, but we extracted merge trees from the function, and so we completely skipped the alignment step because merge trees are invariant to these alignment procedures. We tried the same classification case study, and basically we got better performances. The second application is in the field of medical imaging. In particular, this subfield of medical imaging, which is called radiomics. Basically, there are some substances which are able to interact with tumors, and in this way, there are some tools that can take pictures of tumors. And so, for each patient, we have one picture for every lesion of the tumor that he has. Then, each one of these pictures is embedded into a high-dimensional Euclidean space with the extraction of some features that are called radiomic features. Basically, I mean, there's super study, there's a lot of literature on those, and there are going to be things like the average intensity, the max intensity, the minimum, the variance of the intensity by pixel aggregated in some fashion, and similar stuff. And so this means that every patient is then transformed into a point cloud embedded in some high-dimensional Euclidean space, so that the dimension of the Euclidean space depends on the radiomic features that we select. And the cardinality of the point cloud depends on the number of lesions that the patient has. What we did is basically we represented with this point cloud with hierarchical clustering dendrograms, so with merge trees, and then we took the pairwise distances with a slight variation of the metric that I defined. Then, on top of these pairwise distance metrics, we obtain a clustering of the patients. And basically, the key point is that we were able to interpret some clinical variables in light of this clustering structure. Okay, and that's pretty much it. There are some things that I would like to carry on working. For instance, it would be very nice and would surely extend the number of situations in which these tools can be employed if we get some more feasible tools that can still retain some stability properties. In particular, approximation algorithms, either for the interleaving distance or for the edit distance that I defined, or even some statistics defined on top of merge trees, but which can still distinguish between merge trees and persistence diagrams. Then I would like to still investigate the structure of this metric space of merge trees, because I believe that the algorithm that I defined to approximate the Frechét means can be framed into some kind of gradient descent structure. And also I want to see if it's possible to define some principal component analysis or regression techniques. Then lastly, the edit distance that I propose works for more general graphs than just merge trees. So, and I would like to see if there are some computational tools with which we can work with RIB graphs, which sadly enjoy much weaker ordering properties compared to trees. So this presentation is basically based on this work, but some of his slides are taken from other works. For instance, the two applications are contained in these works. The stability result is in these works, and so on and so forth. And with this, I conclude, and I thank you very much for listening.
All right, so before we get to questions, please briefly unmute yourselves and let's applaud for Matteo. All right. So questions for the speaker?
Hi. What is the thing? Yeah, first, thanks for a really nice talk. So if I understood it correctly, your edit distance is like a Wasserstein version of the other edit distances that are out there.
Kind of.
So is it a Wasserstein or for general P?
No, it's just for P equal 1. And in spirit is kind of the Wasserstein distance, but in truth, it behaves quite differently. And the main reason for that being the fact that it's not based on persistent pairs, so it does not match the persistent pairs, but is based on kind of the weights that we obtain, which are kind of the relative positions of the persistent pairs, if it makes sense.
So these weights, are they just lengths of edges, or do you define them? I didn't quite catch that.
Yeah, they are just length of edges.
Okay.
You take the merge trees, you truncate them, and at some height, for instance, k, and then the length of this edge would be the difference between k and the height of this vertex here. The length of this edge here would be the difference in height between the two vertices that delimit the edge.
Okay.
In this kind of, oh, sorry, go on.
I know you can finish. I had another question, but
okay. Try to convey the difference between just matching the persistent pairs. I think this is a nice example. If you see these two merge trees are kind of, you can imagine that this merge tree was obtained by some kind of downward oriented parabola. Okay, you have two local minima which merge in a local maximum. Okay. This one is just the same function, but translated downwards. Okay. The two persistent diagrams would have basically the same shape, but their coordinates would be translated by some factor on the birth and some factor on the death coordinates. But they would be just the same shape, okay? Just with a translation vector, we would be able to match one with the other. But the key point is that you need to match every point in the diagram with every point in the diagram of the other function. Okay, like here, you need to imagine that you need to match all the points of one merge tree to the points of the other merge tree with the interleaving distance, roughly. Vice versa, with my edit distance, you modify the length of the edges. And so if you take this edge here and you make its length, increase its length, you are actually at the same time moving downwards all the other vertices in the tree. And so instead of matching all these vertices, you just need to slide this vertex downwards and the trees become the same.
Okay.
Okay, so it's more focused on the relative positions of the persistent pairs instead of just matching the persistent pairs.
That's interesting. And I think that's probably at least a partial answer to my next question, which is going to be, there's this paper by Cordona, Curry, Lam, and Lesnick about Wasserstein distances for merged trees. I'm not sure if you're familiar with that, but they define some.
Is it?
Right. Yeah, that's the one.
Okay.
Yeah, I was going to ask about the relation between their, let's say, P equals 1, so L1 distance, and yours, but it sounds like it's different in what you just described.
Yeah, exactly. That would be my answer.
Okay.
I would be very interested to see if I can come up with some kind of inequalities like the one I obtained with the interleaving distance, but still I haven't put my head on it. But the main difference, I believe, is that one that I just described.
Okay, great. Thanks.
Matteo, I wanted to ask a question, and this might be related to non-uniqueness of Frechét means, but the space of merged trees with this distance, do you know, does it have one-dimensional holes? Like, does it have non-trivial pi1 or not?
No, you can contract every tree to the tree with just one vertex.
Sure, but that's saying that it's like connected. Like,
Sorry.
like, is there a canonical way of doing that, I guess?
Yeah, I proved that it's contractible. You can.
Oh, it's contractible. I see.
Yeah.
Okay. Huh. Interesting. Because do you know this? This is quite a different setting, but shoot, there's this paper by Bellera, Voteman, and Holmes, where it's a different space of trees, and they prove that it's cat0 negatively curved, and therefore you always have unique Frechét means. I mean, so here you're still contractible, but you don't have unique means. Interesting. Okay. I don't know if you have any more comments there, or I'll just have to think about it more. I didn't really ask the question.
I believe the main thing is that they somehow are able to rely on the Euclidean distance in like the one they have they rely on the Euclidean distance with the inner product, while I have to rely to the Manhattan geometry, the one norm distance. So you can take very different paths with the same length. And this is the main difference between their metric transported to unordered and unlabeled trees and my metric. And the fact that I need to rely to the one norm is again linked to the stability properties. Because think about having just this merge tree here. If I insert a lot of order 2 vertices, and so I split it in many small segments, okay, then contracting it becomes I can contract it faster, faster, and faster. So the norm, suppose this is at the beginning is it has norm 1, it has one length length 1 edge. Then if I split it again and again and again, the edge becomes so smaller. Then if I square them, then I cannot distinguish it from the merge tree with just one vertex. I can contract it super fast, if that makes sense. While if I take the one norm, this doesn't happen, because contracting the whole thing, all the small little pieces, is the same in the end.
I had another question. So before you got to your slide on computations, you briefly mentioned that there was a comparison, I think, to maybe Wasserstein distances between persistence diagrams, but you intentionally skipped over that. I was wondering if you could say a little bit more about that.
Yeah, I basically is what I've said before, that we have this bound, which is that the Wasserstein distance is still less or equal than the edit distance multiplied by the cardinalities of the trees. Why? Because like here, the Wasserstein distance potentially is much bigger than the edit distance, because I need to match all the persistent pairs between the two diagrams, while with the edit distance, I just make one modification, which potentially is much smaller. So this bound cannot be improved. And if I take two functions which are different but just by a vertical translation, we are in this situation.
I see.
It was, I believe, I mean, for me, it was very interesting to come up with these results. And also, I really wanted to prove also the stability results, because the behavior of this metric was different from the behavior of the metric of persistent diagrams. And so I wanted to have kind of a formal way to see that what I obtain with this metric is still interpretable, is a good result. It makes, it behaves reasonably. It has some kind of continuity. It does not do strange things when working with functions.
Any further questions? Oh yeah, please go ahead.
Yeah, I had one more. I was just wondering about NP hardness, because I know that for these, let's say P equal infinity distances, often it's NP hard to compute them, but I don't have a good feeling for what happens when you have these Wasserstein or sum-like distances. So have you thought about that? Do you have any ideas?
I mean, I know that the edit distance for merge trees without the constrained version that I talked about is NP hard. And in fact, the implementation, as well as the one for unlabeled and unordered trees. And in fact, their implementation in terms of binary linear programming, the cost is very, very similar to the one that I obtain. For Wasserstein metrics between persistent diagrams, to be honest, I don't know. I expect them to be at least somehow better. Not, I wouldn't say, but this is just a gut feeling, not significantly better, at least naively. And I see this because the edit distances between the merge trees that I talked about in the beginning, the one which then resort to a polynomial approximation, are kind of similar. They are kind of the equivalent, or let's say the immediate equivalent of the Wasserstein distance for persistent diagrams. And even in that case, they resort to a constrained version. So I believe that even for the Wasserstein distance, maybe there are super good implementation and stuff like that, but the computational complexity is not too far apart. But this is just my gut feeling.
When you say for persistence diagrams, isn't that polynomial time? I was thinking merge trees is different because there's this all this extra structure, and that's what makes it hard.
Well, I believe that in one of the papers about the merge trees, they say that the fact that they can constrain the search space makes it slightly faster. But again, I remember this, but I wouldn't bet on it. Let's put it this way.
So which distance was this? Some edit distance?
Is this one.
So slightly faster. Does that mean still NP hard or exponential time algorithms, or?
Yeah, but then they resort to the constrained version of the edit distance, which is a polynomial. It is not clear, at least in that paper, how this impacts the instability of the metric. But they basically, I believe they constrained subtrees to be matched, and they make some strong constraints which turn this algorithm into a polynomial one.
Okay, I get it.
State instability, but it's not clear by how much.
Okay, thanks.
Any last questions?
If I may ask a question.
Please.
Thank you, Henry. Thank you, Matteo. I really like the presentation. I have actually an open question in terms of applications. Do you have any comment about the interpretability of the merge trees that you are discussing here? For instance, in terms of visualizations of graphs, is there anything you could say about the noise? I mean, how this representation tell you something about the noise? I mean, everything in terms of applications, or something that you may add in terms of advantages for those who would like to apply your ideas.
Okay. First, in terms of visualization, I think that, at least from my experience, merge trees are pretty good. They work very well if you need to understand the clustering structure of some data set. And so I believe that also for topological summaries, they work just fine. They're better, they're more immediate to understand compared to a persistent diagram, because the persistent diagram contains less information. On the noise, I would say they pick up noise just as persistent diagrams pick up noise. So you're gonna have a lot of, if your data is very noisy, you're gonna have a lot of small leaves in your trees. You're gonna have huge trees with a lot of very smaller branches. In that case, I do believe that there could be some kind of, let's say, bootstrap subsampling procedure that relates to the one for a persistence diagram, where you can denoise with some kind of confidence band around the diagonal of the persistence diagram. So I believe you can do something like that. And the two, let's say, denoising procedures, so removing small features from persistent diagram, and for merge trees, removing like the small branches attached to the leaves, are just analogous, are the same. Like if you fix some bandwidth for persistence diagrams, these translate directly to fixing some threshold for merge trees, and then pruning the leaves of those trees. So in this way, the situation is very similar. For the specific topic of my metric, I would say that denoising trees, it's indeed important, mainly because of the stability property that is sensitive to the size of the tree. So if you have a lot of, let's say, branches, leaves, then distances are going to be bigger. Noise is going to inflate the distance. But for instance, I mean, as I said, you can have procedure to do this, some denoising, even in a statistically sound fashion. Lastly, I last touch on this. If I were to give some interpretability in terms of not just the merge trees, but the metric, I would say that with my metric considers similars merge trees which somehow have a similar shape. Not necessarily they're kind of hung at the same height. Yeah, they're not necessarily that their vertices have the same heights, but the merge trees have the same shape. Like in this case, okay, these have a very similar shape, but they are at different heights. And this is I believe is what my metric really captures, shapes between merge trees. I don't know if I missed some points, if you want some more comments on the applications that I developed, or.
Yeah, I think it was more like an open question, just to get more into what you had in mind about possible things that can be done. But actually on the same thing, let me ask you, what is the next step here on your research?
Was this the next step?
Yeah, what will be the next step? Yeah, what else are you thinking as future work right now?
Okay.
So if you can discuss about it, I know.
Quickly, I will, like, the things that I have in my head are mainly two. One, that I believe that these objects compared to persistence diagrams offer a very big kind of possibility in terms of defining functions on merge trees. So extracting additional information from the path connected components. For instance, you can decompose the homological information within path connected components, because each homology class is in the end located inside one path connected components. And you can find, for instance, this in the decorated merge tree paper of Justin Curry. And so trying to develop frameworks in which we can add some other kind of information on these merge trees related to the path connected components. For instance, also the size of the path connected components could be a sensible information. The second is I would like to work also with the rib graphs, because they really come up in a lot of applications. For instance, I am using them right now here in Denmark to work with some kind of chemistry related structures. And that would be very cool. But the computational complexity increases because of the ordering structure that trees have and rib graphs do not have.
Thank you so much. Thank you so much, Matteo.
All right, well, let's end the recorded portion here. So thanks so much, Matteo, for the nice talk, and thanks everybody for the fantastic questions.